So this morning's session is focused on the restriction phenomenon and its connections to other areas of analysis. So is this not on? Okay. So so this session is focused on the restriction phenomenon, which was a phenomenon first introduced in harmonic analysis by Eli Stein in the 70s. So the phenomenon is the following. So if you take an absolute integral, an L1 function on, say, Euclidean space, we know that its Fourier transform is continuous. So in particular, it can be restricted to any set you like. On the other hand, if you take an L2 function, square integrable, we know from Poncharel that the Fourier transform is just another L2 function, a completely arbitrary L2 function, so it cannot be restricted to any set of measure 0. So, but the amazing phenomenon discovered by Stein was that for certain intermediate LP functions, p between 1 and 2, the Fourier transform of an LP function, while it was not continuous, had some residual continuity in that it could be restricted to some measure 0 sets. But only sets that are curved, sets which are like you could restrict to a sphere sometimes, but not to a plane. So this is a strange phenomenon, and it is still not completely understood, but it has since been discovered to be connected to many, many areas of mathematics, to estimating solutions to PDE, eigenfunctions of manifolds, exponential sums in number theory, and crucially, it was observed by Charlie Fefman, and also Cordoba and Carberry and several others that there was connection to the Guth conjecture in geometric combinatorics and geometric measure theory. But one of the crucial contributions of Jean Bourgain to the subject was to reverse this connection and to observe that if you can understand the geometry of the Guth problem well enough, then you can start making progress on the restriction problem. So Bourgain had this very influential paper in '91, which introduced many new techniques, which are now standard in the subject, studying restriction using multi-scale arguments, wave packets, systematic use of the uncertainty principle, and systematic use of the Guth conjecture. And since then, Jean and others have made introduced many revolutionary new techniques to both the Guth and restriction problem. Jean observed the connection to additive combinatorics, which then exploded as a field in its own right. The induction of scales method was introduced, heat kernel methods, the polynomial method, the sum product theorem has made an appearance, algebraic topology, so there's many new techniques and many new applications. Most recently, of course, Jean with Cyprien Demeter and Larry Guth have proved a very sharp restriction theorem, which is a restriction type theorem, the decoupling theorem, which has since had applications to instance combinatorics, analytic number theory, many other applications. It's a very exciting time for the subject now. And so we have two co-authors of Jean who will speak about some of these developments. And our first is Larry Guth, who will speak on the polynomial method and the restriction problem. So please.
Great. Well, I want to thank the organizers for the chance to speak at this special conference, and also Jean for the chance to collaborate with him and all that I've learned from him. When I was a postdoc, I first learned about some of those papers on restriction by Jean that Terry was talking about. And I was very struck by all the parts of mathematics that he brought into them, or I guess similar to what Terry had said, how for this problem in Fourier analysis, he brings in ideas from geometry, from combinatorics, later from number theory. And then later on, I had the chance to collaborate with Jean on the restriction problem. Started 5 or 6 years ago. And I was coming from a different background. I was doing differential geometry before that. And so when we started to work together, Jean asked me, do you know Fourier analysis? And I thought, well, I taught a course called Fourier analysis. I thought it went pretty well. So I said yes. And he said, good, because then I can write. I don't have to put too much. It'll be easier. So then he started to send me these notes of what he had thought about in our collaboration, and the notes got taller and taller, the stack. And that became our first paper. And in fact, it took me a year or 2 years after the paper was published before I had read kind of all of these notes. And from doing that, I learned a lot more Fourier analysis than I knew when we started. I don't know if I know Fourier analysis yet. Cool. So the restriction problem, I'll remind everybody what it is in a minute. But an interesting thread is that it's been connected to a bunch of different areas of math. And the one I want to talk about today is a connection to polynomials, or a connection to simple algebraic geometry. And the story begins about 8 years ago when, when Zev de Vere proved a well-known striking conjecture. So let me back up a second. So when you have a hard open problem like the restriction problem, mathematicians come up with lots of model problems and cousin problems to try to shed some light on it in different ways. And so Zev completely solved one of these model problems. And not only he completely solved it, but he completely solved it in 2 pages. And not only it was only 2 pages, but it didn't require any background, and undergraduates can read. And the new idea that was in this was a cool trick with polynomials. So they raised the question, like, how much can this cool trick with polynomials that completely solves the model problem, how much can it tell us about the original restriction problem? That's something that I've been working on. And it's difficult to adapt it, and at first it kind of seemed that it was hopeless. But at this point, I can say that, that arguments kind of based on that, arguments using polynomials, have led to a little bit of progress on the restriction problem. And what I want to do today is to explain the connection between polynomials and the restriction problem. Cool. Okay, so the first thing we need to do is to remember what the problem is. So the restriction problem, like a lot of problems in Fourier analysis, is about what happens when we add together waves with different frequencies. So to take a linear combination, so like an integral of some waves, so I'll have some frequencies, phi of omega dot x. I'm going to take a linear combination of these, so I integrate f of omega d omega, and I'm going to integrate over an n-1 dimensional ball. And then these frequencies, there are a lot of interesting choices for phi of omega, but the one choice I'm going to focus on in this lecture is the paraboloid choice. So phi of omega is omega 1 up to omega n-1. And then the last coordinate is omega squared. So phi is parametrizing a paraboloid. And so there are n coordinates here, so it means that x is in Rn. And we're going to take this linear combination. Let's give it a name. I'll call it E of f. And E of f at the point x is this. Okay. And then the question to be investigated, roughly speaking, is how big is E of f in terms of f? So a more precise question is, for which exponents p do we have an LP estimate of the form EF LP of Rn is bounded up to a constant by FL infinity. So for people who don't do, I know there's a lot of harmonic analysts here, but for people who don't do a lot of harmonic analysis, let me say that this is a fancy way of estimating something simple. So this is a fancy way of estimating, to estimate the volume of the set where the size of EF of x is bigger than lambda. So we pick some lambda, we look at the set where EF is bigger than that, and we'd like to know how big is that set, given, say, that the L infinity norm of f is 1. Cool. Okay. So let me draw a picture now to try to explain what's going on here visually. So over here, I'll draw the n-1 ball. And over here, I like to picture Rn. And what I like to picture is a large ball in Rn. OK. And then suppose I want to visualize the contribution to EF coming from a particular frequency, say this blue frequency, omega 1. So I want to try to draw the wave e to the I phi of omega 1 dot x times f of omega 1 on this ball. And it's a wave, so the natural thing to draw are the crests of the wave to help us visualize it. So what I'm going to draw in blue is the place where f of omega 1 times e to the I phi of omega 1 dot x, where that is positive real, the crests of the waves. So there'll be some evenly spaced hyperplanes that look like this. So that's the contribution coming from a single frequency. And then there are other frequencies. So suppose we introduce now a second frequency, and we want to add them together. So we take the contribution from that frequency. It will be a different wave, and it will be going in a different direction. So when we add together these two waves, at a point like this, where the crests line up, there is positive interference. And also at a point like this, where the naders line up, there's positive interference. But at a point like this, there is cancellation. So to add them two up, you can kind of imagine the landscape of that. But now we're going to add together many, many frequencies. So I'll just draw a third frequency to start to give a sense of this. So we add a third frequency. Now we have a third wave whose wavefront looks like this. And already it becomes not so easy to visualize how the positive and negative interference pattern that happens when we add together those three waves. And then our goal is that we're going to add together infinitely many waves, or many, many waves. And we want to understand how much constructive interference can happen and how much cancellation occurs. Okay. So the set where EF of x is bigger than lambda is the set where there's a significant amount of constructive interference. And we'd like to know the size of that set, and maybe also something about the shape of that set. And that's the restriction problem. So let me give a little bit of motivation, and then we'll start to talk about how to prove estimates for this problem. So one piece of motivation to motivate the choice of this phi of omega. So choosing phi of omega this way, these waves are exactly the solutions to the Schrodinger equation on Rn, viewing Rn as space and time, r to the n minus 1 space. And then an arbitrary solution to the Schrodinger equation can be written as a linear combination of these waves like this. And so that's a very important point of view to understand the Schrodinger equation. But to understand arbitrary solutions, we have to have some understanding of what happens when we add up all of these waves with different frequencies. And the restriction problem is one precise question that gets at this subtle issue. Another piece of motivation is that LP norms of not exactly this kind, but roughly this kind, appear in analytic number theory. And Ciprian is going to talk about that in the next talk. And ideas from this field have recently been helpful in understanding that setting as well. Cool. OK. So I think it's quite difficult from the point of view of this picture here to tell how much constructive interference and how much cancellation is going to occur when we put together all these waves. And so there's a different way of breaking up EF into pieces called a wave packet decomposition, which was used heavily by Jean and which is now central to the subject. And so the next thing I need to tell you about is what is a wave packet decomposition. So the first thing that I'm going to do is I'm going to break up the ball into smaller balls. So it's a disjoint union of smaller balls called theta, which each have radius capital R to the minus 1/2. So capital R, maybe I should say. We're going to attempt to study what EF looks like on a ball of radius R in Rn. And if we can understand this for very large values of R, then by limiting or something or another, we can also understand it on the whole space. So we pick some large value of capital R, and then we decompose the domain ball into smaller pieces. So here's the domain ball, and we cut it into smaller pieces called theta. Cool. And then on each of these pieces, we take the function f, and we decompose it in a Fourier series. We decompose it as a sum of contributions with different frequencies. And so one of the contributions might be, I take this theta, and I take the part of f with a certain frequency, which therefore looks like this. And call that f theta v. So the whole function f is a sum over different locations theta and different frequencies v of f theta v. Okay, so what happens when we apply the operator e to this f theta v? It turns out that the output ef theta v is localized in a small part of the target ball, and that's the reason that looking at pieces like this is helpful. So E of f theta v will be supported on a long, thin cylinder. that looks like this. And I'll call it T sub theta v. And geometrically, so it has length r, the same length as the ball, and it has a smaller radius, r to the 1/2. Okay, so the EF theta v is supported in this cylinder. It's very small in the other parts of the ball. And that's the main thing that I want you to know about it. And then remember that F is a sum of many pieces F theta v, so I'm going to draw a few more. So maybe I have a low frequency piece on this ball over here. And a low frequency piece corresponds, EF theta v will be supported on a tube that goes through the origin. And then maybe on this same little ball theta, I'll also take a certain high frequency, and E of this yellow function will be supported on a tube that goes in the same direction as the blue function, but is translated from it. And it's not a fantastically to scale picture. All of those cylinders are supposed to have the same radius and the same length, and they point in different directions. Cool. Okay. So when we break F into different pieces, F theta v, the contributions don't have to be all equal. They're probably not. Nobody said that they were. And so if I draw a picture, what I want to draw in the picture are the contributions that are largest. So it could be that all of the theta v contribute equally. That's one special case. And then the picture should be completely covered with these cylinders. So in every possible direction, the whole ball would be covered with cylinders. Or it could be another extreme that only a few theta v make an important contribution, then we would just see a few cylinders. So this is a wave packet decomposition. Let me check in with the non-experts. Are there any questions about what we've done up to here? Yeah, so this scale in Fourier space is r to the minus a half. So you can play around with this scale that you choose to localize in Fourier space. And the reason that r to the minus a half is the best is the following. If you localize at very, very small scales, then this situation starts to look like this, where the contribution from 1 f theta v will fill up most of the big ball. So that's not very good. The point is we'd like to have pieces that are localized as best as possible. So that's why we start to make this bigger. But when we make this scale any bigger than r to the minus a half, then the geometry of EF theta v becomes more complicated. And the set where it's localized is not a clean rectangle, but like sort of a piece of a rectangle with like a flare coming out in a confusing way. So in John's work on the restriction problem from the early 90s, he uses this setup. And then, so we're interested in the set where EF is big. And you might imagine that a place that has a lot of different tubes going through it is a place where EF is likely to be big, because many different wave packets are contributing to what's happening here. And only one wave packet is contributing to what's happening there. And so he brings into the story some combinatorial and geometric questions about the intersection patterns of tubes, how many different tubes can be on top of each other in some place. And one thing I thought was really cool about the paper is that he gets to this point, and then he kind of switches the worlds of mathematics, and there's a long discussion of combinatorics and geometry to bound the intersection patterns of these tubes. And then with those bounds, he goes back and gets new estimates on the Fourier analysis. Cool. Okay. So the main point of the lecture is going to be to try to explain how this problem is connected to polynomials and a little bit of algebraic geometry. And we have enough background now about the problem that we can start to talk about that. Cool. So it would have been neat if I had time to tell you Zeb's problem and the problem that he solved and how he solved it, which is only 2 pages. So if anybody wants to, you can look it up online. But I don't have time in the lecture to actually tell you that. But I'm going to tell you what are the key properties of polynomials that Zeb used in his proof. And this will, yeah. Okay. And these are the same properties of polynomials that we're going to try to apply. Okay, so first of all, let me make a notation that P sub d is the space of all of the polynomials in n variables, because we're in Rn, and with total degree at most d. Okay, and the first property of polynomials is, roughly speaking, that there are lots of them. The first property is to understand the dimension of P of d, and it says that the dimension of P of d grows asymptotically like d to the n. This is because it was a basis of monomials. For a monomial, I'm supposed to specify n exponents, and basically they go between 1 and d. So there are d to the n choices. Cool. And the second property is something about lines, that if I take a line L and a polynomial in P of d, degree at most d, and if P vanishes at more than d points of L, then it implies that P vanishes on the whole line L. So this is also a totally elementary thing. It's a slightly fancier way of saying that if you have a polynomial in one variable, if it vanishes at more points than its degree, then it must be 0. Yeah? Okay, so these are two totally elementary things, but actually they show that there's a kind of special relationship between polynomials and lines. Because the first thing says that there are lots of polynomials, so the space of polynomials is pretty flexible, it's pretty wiggly. But the second thing says that if you restrict a polynomial on a line, it's comparatively quite rigid, and it's true for every line, no matter where the line is located. If you took a typical space of dimension d to the n, and you only knew something about it at d points along the line, you probably wouldn't be able to say very much about the function. But because of the special feature of polynomials, knowing at only a few points along the line something about the polynomial tells you something. Okay, cool. So where are the lines in this picture? Well, we have these long, thin tubes, and long, thin tubes are a little bit like lines, and so that's how this connection is supposed to go. Okay, cool. So the strategy that we're going to use to find out stuff about EF is called polynomial partitioning. And this is a strategy that comes from work of Metz, Katz, and myself on problems in combinatorics, but problems in combinatorics that people had thought for a while have some similarity in flavor to problems in a harmonic analysis like this one. So here's what we're going to do. We're going to find a polynomial in P of d, and then I'm going to draw its 0 set in red. So z of p in red is going to be the 0 set. So maybe the 0 set looks like something like this. Okay. And it's called partitioning, so I want to think of the 0 set as partitioning the ball into some pieces. The connected components of the complement of the 0 set are my pieces. And they're called cells in the literature. So the next thing is that the number of these pieces is around d to the n. The number of cells. The cells are called O because they're open, O sub I, and the number of cells is around d to the n. And the next property of this polynomial that makes it really nice is that these cells is an even partition. So the integral that we care about, the integral of EF to the p, each cell makes an even contribution to that integral. So if I take the integral over any of the cells of EF to the p, it's just 1 over the number of cells times the integral over the whole ball of EF to the p. Okay, and that's true for every cell. Yeah. Okay, so why is it possible to do this? Well, the hand-wavy argument is that we are trying to choose a polynomial to get d to the n equations to hold, so d to the n cells. And we have d to the n degrees of freedom to play with. So just based on a very naive heuristic about the number of degrees of freedom we have and the number of equations we want to satisfy, it's plausible that we could find such a polynomial. Yeah?
What is a cell exactly?
What is a cell exactly? So Okay, so what I can say is that if I take the ball of radius r and I remove z of p, then this is a disjoint union of O sub i's, and the O sub i's are open. So strictly speaking, if we want them to be exactly equal, once in a while there might be two different components that we think of as one cell. But that's kind of a fine point. For a general lecture, I think it's also perfectly reasonable to think of the cells as just being the connected components of the ball take away the zero set. Okay, other questions? Okay, so I was just arguing that based on a naive counting of degrees of freedom, like a physicist-style argument, it's plausible that there would be a polynomial that does this. The real proof that there's a polynomial that does this is harder than that. And it uses ideas from topology. It's closely related to the ham-sandwich theorem. It boils down to a version of the ham-sandwich theorem that was proven by Stone and Tukey in the 1940s. And I learned about this kind of application of the ham-sandwich theorem from some work of Gromov in differential geometry, which was my background and something that I brought to collaborating with Jean. Okay, anyway. So why is it helpful to cut things up this way? What we're going to try to do is to make a divide and conquer argument. So we've divided the integral that we want to estimate into even pieces. And what would help us to conquer is if each of those pieces is simpler to understand and estimate than the original problem. And the way we might hope for it to be simpler is that we might hope that if we looked at one of these cells, that only a small fraction of the wave packets from F actually enter the cell. And then when we study what's going on in this cell, we only need to pay attention to the wave packets that enter the cell, and so we would have a simpler problem than the problem that we started with. Okay, so I want to try to argue that it's at least plausible that a typical cell would only intersect a small fraction of the wave packets. And here's a helpful fact. A helpful fact is that a straight line can only enter a small fraction of these cells. A straight line can only enter d plus 1 cells because, so I brought a straight line. So every time this straight line goes from one cell into another cell, it needs to cross the variety z of p. So that's a point on the line where the polynomial vanishes. And the polynomial can only vanish at d points on the line, or else it would vanish on the whole line, and it would be contained in the red set. It wouldn't enter any cells. So that means that the line can only enter d plus 1 of the cells. And that's a small fraction of the cells because there are d to the n cells. So each line is only entering a small fraction of cells. Okay. So we might hope at first that each tube is only entering a small fraction of the cells because the tubes look pretty skinny. They're very eccentric. They're much longer than they are fat. But the fact remains that they're not lines, and this distance of r to the 1/2 is quite a big distance. Remember that the wavelength of these waves, I guess I erased the picture before, but the wavelength of these waves is 1. The norm of that frequency is typically on the size 1. So if I look at this orange wave packet, it is sobering to remember that it also has some oscillation. And if I draw the wave fronts, they look like this. This scale is 1, much smaller than this scale, r to the 1/2. So even though these are kind of skinny, their thickness is still quite substantial. And because they're thick, it's actually plausible that almost all of the cells would be localized in here. And so this blue tube could actually go through almost all of the cells. And so the way that we fix that is that we thicken a little bit the red set. So we define W to be the r to the 1/2 neighborhood of the 0 set. And then we shave off this part from each cell. So we define O sub I prime to be O sub I take away W. So I'm going to have to cover this for a little second to draw what I mean on the picture. So W is the r to the 1/2 neighborhood of this variety. So a little bit. the variety was in the middle here. And this whole red set, this whole thing here, is W. Okay. And now that we do that fixes the problem. And we can say that each tube T theta V enters at most D plus 1 cells. D plus 1 of the smaller cells, O sub I prime. So each tube is entering only a small fraction of the smaller cells. Cool. Okay. So now in the analysis, there are several scenarios. And the main scenario is, so we now divided our domain, our ball, into a little region near the variety, which is called W, and some cells which are called O sub I prime. And the integral we care about is the integral of EF to the P. And it could be that it mostly comes from the cells, or it could be that it mostly comes from W. And so there's different analysis in these different cases. And in fact, there are really three scenarios. So the first scenario is the cellular scenario, which is when the O sub I prime dominate the integral. And that means that if I take the integral over the whole ball of EF to the P, it's approximately d to the n times the integral over one of these cells. Maybe not for every single I, but we could say for most I. Okay. And now I'd like to carry out this divide and conquer argument. I know that for a typical cell I, there are only a few wave packets going through that, and I'd like to now study what's going on in each cell and take advantage of the fact that there are only a small fraction of the wave packets. Yeah?
Is D large compared to R, or small, or bounded?
Great. That's a great question. So D is a parameter at our disposal, but it turns out that it is a good idea to choose D to be a large constant. So maybe it's good to imagine a million. And that means that D is actually very small compared to R, because we're interested in taking a limit as R is going to infinity. Nice. Are there questions? Cool. Okay. So suppose I want to focus on one of these cells, O sub I prime, and I want to study what's going on in this cell. And I only need to take account of the wave packets that enter this cell. So I can do this formally as follows. I define F sub I to be the sum of F theta V, but only over those pairs theta V, so only over the theta V's with the property that T theta V actually enters the cell O sub I. And then I can say that EF and EFI basically agree on that cell O sub I prime. Cool. Okay. So then I'm going to run some kind of iterative argument or some inductive argument where we study EFI. And EFI is a little simpler than FI because it involves fewer wave packets. And I'd like to understand how the size of FI compares to the size of F. And here's a simple lemma about that. The sum on I of Fi L2 squared is bounded by D times F L2 squared. So there are a lot of computations in harmonic analysis. I thought in my lecture I would do one. Let's do this computation and check that this is true. So proof of lemma. The key point in the proof of lemma is that the functions f theta v are orthogonal to each other. Let's take a second to see why that's true by remembering what are the functions f theta v. Right, so I took the domain and cut it into smaller balls theta, and for each theta, I expanded f in a Fourier series. So if I take two f theta v's supported on different thetas, obviously they're orthogonal to each other. And if I take two f theta v's supported on the same theta, because they have different frequencies, they're again orthogonal to each other. Okay, so these functions are orthogonal to each other. So now, when I look at the left-hand side, the sum of these norms, the left-hand side is the sum on I, and then FIL2 squared this is an orthogonal decomposition of Fi. So it's the sum of f theta v L2 squared over this set of theta v. So I have the sum on I, the sum of f theta v L2 squared, with the condition that t theta v intersects O sub I prime. Okay, so now actually I have a sum over theta and v of f theta v squared, but some of these appear many times. F theta v will appear many times if t theta v goes through many O sub I prime. But there's not too many that it can go through, because our geometric observation, using these facts about polynomials, is that each tube only actually enters about d of the cells O sub I prime. So this is smaller than d times the sum over all the theta v of f theta v L2 squared. Okay, but f itself is the sum of f theta v, and this is again an orthogonal decomposition. So by orthogonality, this is d times bigger than f L2 squared. Okay, cool. So in the cellular case, the original integral is d to the n times bigger than the integral over each cell. And on the other hand, for the L2 norms, the sum of the L2 norm squared is d times bigger than the original L2 norm squared. And this is the basis of some kind of iterative argument that we could use to understand the f sub i's. So I won't do the whole calculation, but if there's time, I'll tell you a little more about that iterative argument later. Okay. However, this is only one of the possible scenarios. It might be the case that our integral is not dominated by the cells, but it's dominated by W. And that scenario, actually, we're going to break into two smaller scenarios. Let me give a little bit more space. I didn't rehearse this. Yeah. This is a great treat to get to lecture in a room with the blackboards that do this. Okay. Okay. So the second scenario is that the integral is dominated by W. But when the integral is dominated by W, I'd like to distinguish two possibilities. There are wave packets that cut through W transversely, and there are wave packets that are contained in W, and we're going to treat those differently. So the first case, the first of those two, this second case total, I'll call the algebraic transverse case, which means that W dominates the integral, but the tubes that are important are transverse to W. So I'll make a little picture of that. So I have this W, and then the important tubes are transverse to W. Like that. Something that might well happen under the second case is that there could be a lot of tubes that go through a little ball like that. Okay, something like this. Okay. So the good thing about this scenario is that a priori, if we were interested in the yellow wave packet, we had to worry about the whole length of the yellow wave packet. However, by the fact that we're in this scenario, we only have to worry about the part of the yellow wave packet in W, which is a very small fraction of the whole thing. And so we've gained something there. And the way to take advantage of that is to cover W with balls, cover W with smaller balls. And the radii of these balls are much smaller than R. And the observation, because T theta v are transverse, so I drew it in this picture so that each tube only crosses W once. That's an exaggeration. A tube could cross W d times. But nevertheless, each tube crosses W a small number of times. And that means that it only intersects a few balls. And actually, I'll even put morally one ball. Morally, this picture is correct. And this comes back to Phil's question or comment about the relative size of D and R. So each of these tubes is crossing D smaller balls. But the smaller balls are much, much smaller. You might think from my lecture that they would have size r to the 1/2. And for technical reasons, they have size more like r to the 0.99. But nevertheless, these balls are much smaller than the original ball. And in return for getting to look at a much smaller ball, we only have to pay that each wave packet is intersecting 1,000,000 balls, which is almost like 1. OK. And then in this scenario, we have to analyze what's happening on each ball. And we do that by induction on the radius. OK. And then the third thing that can happen is that the tubes can not just cross W, but tubes can lie in W for almost their whole length, or for their whole length. So the third scenario is the algebraic, call it algebraic tangential scenario, where the tubes lie in W almost for their whole length. And I'll just make a picture of this. So to make a good picture of this, I want to draw W as a two-dimensional slab, say in R3. And then inside of this slab, there are a bunch of wave packets that are running in different directions. OK. So what's good about this scenario? Well, the whole problem has been reduced to a lower dimensional surface. And also all the tubes are in the lower dimensional surface. And that means that it actually is quite similar to the restriction problem in lower dimension. Especially if the surface was flat, it would literally become the restriction problem in n-1 dimensions. So in this scenario, we're going to do induction on the dimension. OK. So those are the three scenarios. We cut up our domain with a polynomial. If the mass comes from the cells, then we've done a good divide and conquer, and we've broken the problem into simpler and smaller subproblems. If the mass is concentrated on the surface W, but the tubes are going transverse to W, then we've essentially broken our problem into some separate problems on smaller balls. And if the tubes lie in W for their whole length, then we've reduced our problem to a similar problem in a lower dimension. OK. So let's pause here and see if there are any questions about, so we do this, and then what we're going to do is we're going to keep iterating this, and things are going to get simpler and simpler. And then somewhere at the bottom, there'll be an inductive assumption where we have some very simple bounds and simple cases. We'll put it all together and get some estimate for EF. And that's the plan. OK. So are there any questions about this strategy? Yeah. Yeah. So the dimensions in this picture are, this is the thickness of W. So this is r to the 1/2. And this is r. So remember that W, so this thin direction in this picture is corresponding to this thickness in that picture. So W, remember, was defined to be the r to the 1/2 neighborhood of this hypersurface. So it has one thin direction of length r to the 1/2 and n-1 large directions of length r. And for a general audience, if you consider yourself to be a general audience, you could imagine it being basically planar, but it can be somewhat curved, and on the technical level, that makes things a lot harder. Other questions? Yeah.
What happens to the LP norm on the cells in these 3 or 4 tubes?
So in case 1, the LP norm on the cells is described by this. In case 2, we're not going to pay attention to the cells anymore because W is making the leading contribution to the LP norm. And instead, we're going to cover W with these balls. And the analogous thing that we can say about the LP norm is that we can say that the integral of EF to the P over the big ball is bounded by the sum over these smaller balls of the integral of Bj EF over the smaller ball. And where these smaller balls just have to cover W. They don't have to cover the whole big ball. Good. Other questions? Yeah.
Are you allowed to lose the power of R when you write this inequality?
The question is, are we allowed to lose a power of R when we write this inequality? So in other words, what if we had this? Would that be okay? So the answer is yes. This is a little bit more of a for the experts question. But let's say that the radius of these smaller balls is r to the 0.99. And then if we lost a small power of r here, but we got to put r to the 0.99 there, and then we iterated this, then the total amount that we would lose would be bounded by a geometric series times epsilon, and it would be okay. So this would be okay. I'm not sure this is just, this is also true without a loss, but we could have taken a loss there. Good. Okay. So let me try to describe a little bit about what happens when we iterate this. I just described doing this once, but we're actually going to do this many times. I'll try to make a picture of that. So let's erase these numbers. It's true that I didn't explain these numbers. Unfortunately, I also will not get to explain these numbers. So I want to describe some procedure for estimating how big EF is. And then when you carry out this procedure, you do a computation, which is 3 or 4 pages long. And at the end of this computation, you get these numbers. But I don't want to do the computation here. And I don't think, actually, that you want me to do the computation here either, really. Okay. Right. So we started with a big ball. And then any of these things could have happened first. But for the sake of argument, suppose that the first thing that happened was the cellular case. So this big ball was cut into some cells, say 4 cells. And then we look at each of these cells, and we carry out the same argument again. And so maybe this one, we're again in the cellular case, which means that this region is cut into smaller cells. Maybe this region is cut into smaller cells. But maybe here we might end up in case 3, the algebraic tangential case. So in here, there's some kind of slab of W with a lot of tubes in it. OK. And then we keep cutting, and maybe here we cut some more. And over here, we have case 3, a slab with tubes in it. So this is a rough picture of what happens when we iterate this argument and do it many times. So what do we gain from this? Actually, so I wanted to say about this that this picture reminds me of, or is inspired by, the Calderon-Zygmunt decomposition, Calderon-Zygmunt stopping time decomposition. But the new wrinkle compared to the classical Calderon-Zygmunt decomposition is that in the classical situation, you take a cube, cut it into smaller cubes, take them each and cut them into smaller cubes, and maybe stop if you see an interesting structure. And instead of cubes, we're cutting things up using curved surfaces given by polynomials, and the curved surfaces are adapted to the function f. And so that's the new wrinkle. So wrinkled Calderon-Zygmunt decomposition. Okay. So in the time that's left, I'm going to try to tell you a little bit about the calculation that goes on when we carry out this iteration. Yeah. So the first remark I'd like to make is that if case 3 never occurs, case 3 is the algebraic tangential case, the one up there. If that never occurs when we carry out this process all the way down, then we get a very nice estimate. We get a bound for EFLP, it's bounded by FL infinity, for all p in the conjectured range. Okay, so this is the range of the Stein conjecture. On the other hand, this case 3 certainly may occur, and when it does occur, we don't get such a good estimate. This is not close to proving the full conjecture. This would be the full conjecture if somehow you could tell me that case 3 never occurs. Yeah, or for some functions, case 3 never occurs, and for that class of functions, they obey the full conjecture. But it's certainly true that for some other functions, case 3 does occur, and we're still far from proving the full conjecture. So if case 3 does occur, then I can not say anything nearly as exciting. But what I can say is that we get some, it gives us some information about the shape of the set where EF is big. When case 3 does occur, and if EF is big on a large set, that set needs to be mostly contained in these things. There's a little bit of leftover in the zone where case 3 doesn't occur, but the total contribution of that leftover is acceptable. And if there's a counterexample, it needs to be mostly organized into these small neighborhoods of low-degree algebraic varieties. And so that new information, that the small improvements in the bounds come from having this new information about the shape of the set where EF is big. Yeah. I just realized what people were asking about when I erased the numbers. The plan was I was going to walk over there and tell you about the numbers for a minute early in the talk, and I forgot to do this. So then when I erased the numbers. Okay. But they weren't that interesting, those numbers. I can summarize what they showed. They showed that the new p are slightly bigger range than the old range of p. That's all you would have remembered anyway. Okay, cool. So if 3 never occurs, we have a good bound. If 3 does occur, we have a better picture than we had before of the shape of this bad set, and that's something that we can leverage to get better information, better estimates about the size of the set. Cool. Great. Well, this is the story I wanted to tell you, so thank you for your attention. Let's stop here.